כבר מעצם תוך השביל במשרד.
זה אמור להתחיל.
רשום אצלי יש לך ואחד, זה מה שהייתה חסרה בדבר.
כן.
אתה אומר בהתחלה נתחבר ואחר כך או ש...
איך שלא ככה, כמו שאתה מעדיף, יש מספיק זמן לכל.
בוא נראה שזה מתחבר.
אוקיי.
תראה שאני בדרך כלל לא לקחתי יותר, אבל זה אמור להחזיק
אוקיי.
הרבה שעות.
אוקיי.
הזמן הרסמי של ההתחלה זה
10:45. רגע, אז זה שנייה.
זה לכאורה הכי טוב כל פעם. צריך לקבל אותו מחדש.
חמישית, עד הסוף חמישית. אם זה עדיין שם, אני לא הייתי פה 3 שנים.
הוא ראה מישהו?
מצוין. או, אלי בדיוק. ברוך הבא.
ברוך הבא להם.
שלום, יופי. אני אראה לך...
כן.
הוא הזה שהסטודנט שלך? אתה לא יודע כמה. צעקתי בטלפון לאביעד.
אתה יודע.
לא, זה ממש, אתה... אני ממש, אני אדם די רגוע, אבל לפעמים אני לא כזה רגוע, אני יוצא משום משקל, וזה פשוט עצבן. התחלתי לדבר עם המזכירה, זה לא אני, זה המזכירה הראשית. באתי עם המזכירה הראשית, אמרה, זה לא אני, זה אביעד. התחלתי לאביעד. לא, כאילו, אני אומר להם, תשמעו, אני מבין את העיקרון, כן?
בסדר.
אבל במקרה הזה, אתה יודע, אני אומר להם, אני מארגן את האירוע הזה, אני יודע כאילו מה... הוא אומר לי, חשבתי שזה סתם מישהו שנרשם שלא קשור לכלום. אמרתי לו, תשאל אותי, כאילו, אני מארגן, אני בודק את זה. מה שצריך. קיצור, אבל זה בסדר, אני מאמין שזה יעשו פעם.
תודה, לא נורא, הוא באמת שמח להגיע בלי קשר, לא,
זה סתם, זה יצבן אותי שאני עושים לי דברים, כאילו, אני מארגן של קולוקיום, דברו איתי, כאילו, אל תעשו, לא ידענו, לא יודעים, אז תשאל פה, כאילו. נחמד, דיברתי איתו קצת.
אם יש לכם עוד זמן, זה כיף. לב הוא טיפוס מוסי, הוא אוהב את ה...
הוא התחיל, כאילו, הוא ישר התחיל עם פוליטיקה, כאילו. היה איזו הזדמנות, מיד הוא אמר לי, אני חושב ככה, אבל אני לא, אין לי דעות, אני יודע שהוא חיפש כאילו מישהו להתווכח איתו, אני לא יודע מה התשובה על השאלות האלה, אני לא יודע, תשמע, אולי אתה צודק, אולי אחרים צודקים, אני לא...
הוא יצא מפה מאוד מתוסכל אם אנשים יסכימו איתו.
אוקיי.
תגידו לו תודה, היה מעניין, הוא מאוד יתאחד.
הבנתי, בסדר, אז אני אדאג שזה לא יהיה. לא, הוא כבר התחיל להגיד לי, וזה אמרתי לו, טוב, מדדנו את האופרטור הזה, איזה אומר לי, לא באמת, כאילו איזשהו, אתה יודע, איזשהו ZXZ כזה. כן. הוא אומר לי, טוב, איך מדדת? בסדר, מדדתי ZXZ, הוא אומר לי, לא, זה לא נחשב. אתה מדדת Z, מדדת X, מדדת Z, לא מדדת ZXZ, זה לא טוב. לא, זה בסדר, אמרתי לו, תיאורטית, אני גם יודע לעשות מה שאתה אומר, אבל... לא אצליח לעצבן אותי באמת. אבל יש לו עוד יום שלם.
כן, כן, יש עוד סיכוי.
טוב, רגע, אני גם חוזר עוד כמה דקות.
כתבתי לו, הוא רוצה.
כן? וואו, כן.
הוא אמר לי לשאול אותך, אמרתי לו, שאלתי.
הוא לא שלח לי מייל בדבר, מסתכל. יופי, תודה. היה לי מאוד נחמד.
אני מקווה שיצליח.
אתה יכול לשלוח לי אולי את ה... אני רוצה לעבור על המאמרים שאמרת לי של יותר מדעי המחשב כזה.
תזכיר לי בבקשה, באיזה הקשר?
אנחנו ב-PQC בהתחלה יש שם את ה... ביום הראשון ראיתי שיש שם ממש מדמח.
כן, כן.
אני רוצה כאילו תוכל לשלוח את הסילבוס שאני אוכל לעבור על הנושאים.
את ה...
כן, כן.
כן, כן. אני שולח לך עכשיו. מקסימום תשאל את עמי, זאת מתמטיקה אלמנטרית.
לא, תעמית, הנה הוא פה.
אני המדע למחשב
כן, אתה ראש תחום
ראש תחום לא, מה, פוסט קוונטום קריפטוגרפי זה שטויות. אני לא יודע באמת חבל קריפטוגרפיה.
לא, אבל אתה תקרא את זה, אתה תבין.
הסוף זה אלגברה. בשנה הבאה קיופיד, בסדר? נסתכל על זה מספיק מזמן. תודה רבה.
אני אכלתי כזה.
זה חדש, אני הכרתי גם קורונה.
נכון, זה יותר טוב.
לא יודע, משהו לכל הארץ, גם אותו דבר. אבל זה יותר עדין, כאילו, מרקם יותר נעים.
אוקיי, יש כאלה שהם דחוסים בחלבון, הם קטנים ואז הם נוגעים.
בדיוק. גם פחות סוכר. רגע, אני חושב שזה רק טוב.
כן?
יש סוג אחד שהוא טוב, הוא לא משהו.
חודש בלונדון, 2 בבריסטול, עכשיו עוד חודש בבריסטול, זהו.
16 עד 30.
אני כאילו...
לא לשאוב משהו.
היי, מה קורה?
נשמח. זה מקום מסודר, אפילו לאנצ'ים סטודנטים, כמו שנתתי קולוקיום בהרווארד, אז כנראה שהרעיון בא משם ממש. קל להשוות סטודנטים בהרווארד ופה. קל להשוות סטודנטים בהרווארד ופה.
את יודעת ששעת התחלה רשמית היא 12:45?
נראה לי
תקשיב, אני אף פעם לא יודעת מתי אתה מתחיל פה.
סטודנט
פעם
שלי, אני
שעברה, למה? היי, ראיתי עוד משחק. וואי,
גם יש לי.
כתבתי אותו.
זה נכנסת ממש לפיזיקה של...
אנחנו נסתכל. נעבור על זה, אבל...
כן, כן, עמנואל...
מתי את חייבת לשלוח?
הוא יסדר את זה.
תקשיב, פעם שעברה
הרבה שנים
אנחנו
של קולוקיום.
הגענו ב10:30, והיינו פתוחות 10:30, 10:30 באתר.
לא, זה הבעיה של אור.
לחמם את הדבר, תראה מה.
אבל... כן, כאילו אתה רוצה להגיד לנו.
הוא פרויקטורה.
כאילו מנדים אותנו.
יש.
כן, נכון. למרות שבכמה פעמים ביקשנו מעט יותר שכזה לא קורה.
ניתן לה... שלחתם או שזה באיזה שלב?
הגשנו... אבל הניסוי, אותו עוד לא שלחנו. עשינו ניסוי פעם אחת. הייתה בעיה באינטרפרמטר, לא היה מספיק טוב. אינטרפרמטר של אקסאי, זה לא פשוט.
אני הולך למחוא כפיים, יש למחוא כפיים, יש מישהו
לאט לאט אנחנו מתדרדרים, אתה יודע.
צריך לעשות משהו.
בחדר היה צריך לטפל בזה.
אם אתה שותה קפה. מילא היה ברזילי, אני היה סבבה, אבל לא מדברת עכשיו.
כן, תעשה אבל, לא, אתה לא מסכים אתה תשים את זה, תישאר כל שני.
Good morning, everyone. I'm honored to present this week's colloquium speaker, Professor Lev Weidman. Lev did his PhD at Tel Aviv University under the supervision of Professor Yakir Aharonov. Then he continued to postdocs at South Carolina, Tel Aviv, and eventually got the chair position. He is the chair, the Alex Magui Glass Chair of Physics in Complex Systems, and also a visiting professor in the past at Oxford University, Bristol University, and Chapman University. Lev has made many seminal contributions to the development of quantum foundations and quantum information, much before the current interest in this topic. He has many contributions. I'll mention the ones which I think are most important for him. The development of weak measurements, weak values, protective measurement, other types of non-local measurements, the interaction-free measurement, which he will discuss, and its offspring counterfactual protocols. Lev also suggested a local description of the Aharonov-Bohm effect, and in fact strives for a local description of nature based on fields and potential, based on fields rather than potential. And no one is perfect, so Lev is also a strong proponent of the many-word interpretation. Please, Lev.
Yeah. Thank you, Eli. I'm very happy that you could present me here as a member of Bar-Ilan University, and also you mentioned that I have this chair. I think essentially this is probably the only official thing which I have now, because I'm emeritus from just more or less now. But the chair in Tel Aviv, they give you another 2 years to be a chair, even after the retirement. So this is probably my official. And okay, so I don't think I have much time to discuss other issues. Let's talk about my talk. And I'm doing research, something which surprises me and which looks unusual. And in this topic, in fact, I was surprised a few times because I even changed my mind a few times. So I will start with Elitzer-Weidman interaction-free measurement, the Bohm problem, which I think it's pretty paradoxical. This is one of the reasons why I believe in many words, because it's there are many words that in one word you find the Bohm, and in another word you explode it. Because if to find the Bohm without touching it, it's impossible. So this is my reason for many words, but I probably will not talk about it much today. So I will first talk about finding objects. It doesn't have to be a Bohm. Then it was surprising, very surprising for me, that apparently there is a method also not just to find the Bohm object without touching it, but also to find that there is no object in some place without being there. I think this is more difficult, but it looks like it's possible. Then relatively recently, I combined these two things to make counterfactual communication. I will explain what counterfactual communication is. This communication is not very efficient. I will describe the method how to make it efficient. There is quantum Zeno effect, which is also interesting and somewhat surprising effect. So after presenting all this, I will show you some amazing story that using quantum mechanics we can do miracles. But I will say that it looks for me too good to be true, and I will discuss some doubts. So really what I will present you in the first part of my talk is really true. And I talk about these doubts to Yakira Aronov, and he didn't believe in my doubts, and we look like corrected the method. So then I will, after presenting our patch to all these counterfactual communication protocols, which will have some difficulties, I will say how to repair them. And in the end, I will present a new doubt, which I have now. It's still not published, but I'm not sure that our correction is good enough. Okay, let's start. So Adi Litzur, long time ago, walking in, I think, near the Lev cafeteria, he asked me this question. In fact, he asked several people around, and then the question seems you have an object, and this object is kind of super sensitive bomb or mine. Whatever touches it, it explodes. Of course, it cannot be, you cannot see it because see, it's photons going, and so every photon will explode it. And the question, can we found it without exploding? If the only interaction with an external world, it's only through explosion, it seems completely impossible. But it turned out that quantum mechanics allows a very simple solution of this problem, how we can find this bomb without exploding. You think this is the only way it interacts with the world, but we can find it without exploding. And so sometimes you can say maybe it's simple. If you have two boxes and you say there's a bomb in one of them, and you open one of them, you see it's not there, you know it's another one. But here we don't have this promise. There is no promise. The bomb might be here or might not be here. And maybe it's not at all. So the question, can we find it in a particular place without exploding? And so the solution, in fact, is from very simple quantum experiment. Mach-Zehnder interferometer. Mach-Zehnder interferometer, which is tuned to destructive interference to one of the detectors. Mach-Zehnder interferometer was really a classical device for light 150 years ago or something like this. Aspect and Grandier were first to make it with single photons. But people do it with neutrons, in some way with electrons, so this is possible to make this kind of interferometer. And you see, if we test that there is nothing everywhere here, except this place we don't know, might be a bomb here. So if I send a photon, this cannot click if there is no bomb. However, if there is a bomb, then this is a quantum state. It goes to all these places, and in fact there are three places it ends. It might end at bomb here and here. It can end here. So we can get a click here. If we get a click here, there will be no explosion. We cannot find a photon in two places. If it's here, it clearly was not here. So when we get this click, we know that the bomb is present. Because if there were no bomb, this cannot click. So this click allows us to know that the bomb is present. And what is surprising, we know that the bomb is present, and we know that nothing was near the bomb. Because the only thing which could have been is this photon, and this photon reached here. If it would be here, it would be explosion, it never come here. So this is interaction-free measurement because the photon could not reach detector D if it interacted with the bomb. Roger Penrose got a preprint from me in one of the conferences, and I was lucky he put the chapter in his book Shadows of Mind, and he also made some story, and he coined the term counterfactual. Well, why I say it's counterfactual? Because IFM is possible because the photon could have interacted with the bomb, but in the event of success it didn't. So this is a counterfactual event, and this is kind of counterfactual process. So in the title I talk about interaction-free measurement and counterfactual communication. Let's just define what I mean by counterfactual communication. Of course, it's everything quantum. I believe everything is quantum. In every communication, quantum, we talk classical, we have Alice, quantum, Alice and Bob, and they have a channel, and we send something in a channel. Particles which some records on them, or maybe even just the presence of a particle will tell us the message. Alice can send or not send a particle. This is really kind of the method which we will use. So there is a channel, we can send something or not send something. So this is standard communication. What's called counterfactual. Counterfactual, in principle, the particle can go there. We have a channel. In fact, usually the channel is bigger than this channel. There are several channels. But when we get the information from Alice to Bob, and Bob got the information in this allowed, there is a protocol. Sometimes doesn't count. Sometimes it counts. We allowed classical communication, which is not secret. All this is supposed to be secret. We send a secret message through this channel, and when we send it, nothing is there. It's empty. So this is what's called counterfactual communication. It's very much like interaction-free measurement. We find that the bomb is there without particle being there. So here we somehow send information from Alice to Bob, or from Bob to Alice, in fact from Bob to Alice, without anything in the transmission channel. So let's come back to this IFM of bomb, but we don't need bomb, we just need any opaque object, shutter. So this is our interferometer. It can be blocked or not blocked. So when it's blocked, this can click. When it's not blocked, it cannot click. So when it clicks, we know that the shutter is here. And let's say Bob will send information to Alice by putting the block. Putting a block, it's bit 1. So this is counterfactual transmission of bit 1. If Alice gets click here, photon was not in the channel. Here, somehow, maybe you can see that there is all this region. There is the projector doesn't give you the colors. All this side is Alice, and transmission channel is just all this area pattern from here to here, and all this Bob. The same here. So there is an empty space between Alice and Bob. This is where the photon can go, or maybe also here. And nothing goes through, because if this photon comes here, it was not here. So we know that the object in O, but the photon was not here. Because it would be here, it would never come here. And this counterfactual transmission of bit 1. Yes?
Okay. Sometimes a photon goes. I mean, we probability have a photon either goes or doesn't.
When photon go here, Alice will never get a click. So the transmission happened when Alice get a click. Alice get a click, she knows the Bob put 1. All other things are not count, but when she get a click, so it's transmission.
It's a post-selected even.
Yeah.
Okay. So now, okay, so this is one story, but then I was surprised. In fact, here was something even more complicated, but I translated to this simple scheme of doing the opposite, to finding that the place is empty. Now I want to find that the place is empty without being here. So now I'll build a bigger, a little more complicated interferometer, nested Mach-Zehnder interferometer. There is a big interferometer, and there is another small interferometer inside. and it's tuned in such a way when it's empty, the photon doesn't continue to the big one, it just go out. So essentially it can go only on the left, because everything which go inside go out. However, if I put a block, then of course there is no interference here, something go here, and I arrange all this, there are 1/3 here, 2/3 here, I arrange it in such a way that this one cannot click when it's blocked. When it's not blocked, of course it can click, because there is a beam splitter here and there is a beam only from here, so it can click. When it's empty, it cannot click when it's not empty. So in the case we get a click, we know that the object is not in O, because if it would be in O, click is impossible. And again, also we know that the photon was not here, because if it would be here, it would never click. So we have these two elements. And this is counterfactual transmission of bit 0. When Bob puts a shutter, it's 1. When he leaves it open, it's 0. So it's counterfactual transmission of bit 0. And maybe you can see this is Alice here, and this is Bob area, and in this case, nothing go here because the photon is here, so we must took this part. So I combined it relatively few years ago with an even more complicated interferometer, which does two things. In the end, we have these two detectors. Here there is one interferometer, here there is another interferometer, and this is our nested interferometer. This is kind of this big story. I arrange it in such a way that when it's blocked, then of course there is something go here, and then all this transmission arranged in such a way that there is a destructive interference towards this detector. However, when I take this shutter out, first this inner interferometer is kind of destructive toward here, so everything which come here do not continue. But when all this small interferometer arranged in such a way that this cannot click and only this can click. So if I consider cases when this click, I know that the shutter is there because it cannot click when the shutter is out. When I get this click, I know that the shutter is not there because it cannot click when the shutter is in. So this is transmission in case of success. In many cases, the photons are lost. They can be lost here, here. Many places the photon can be lost. 80% of photons are lost. But when Alice get click here or get clear, she get information 0 and 1 from Bob. So this is kind of inefficient counterfactual communication. In both cases, nothing goes through the transmission channel. Here we can definitely see this is transmission channel. Nothing passes through when Alice gets these clicks and we get this information. Now, somehow it was my mistake. I saw that interaction-free measurement, the maximum efficiency, 60%. I didn't realize that if kind of repeating it many times, we can use Zeno effect and make it as close to 100% as we wish. So, you remember, this one interferometer was interaction-free measurement, but if we'll make a chain of them, and every time only small portion of part of the wave goes through, and then a little more and a little more. In the end, everything goes through. Now, if I put a big shutter or shutter everywhere, then essentially I test: did it pass here or did it pass here? And you know, in quantum mechanics, if you test is something happened to know, this is what Zeno effect. It will never happen. So, testing this, I can prevent the photon to go from the left to the right. It will stay in the left, and finally will end up here. So, if I get a click here, I know that the shutter is placed. It cannot click here if there is no shutter. And now it's very efficient. There is very tiny probability that the photon will be absorbed here, because there is every time the probability roughly about 1/n. That it's we need amplitude 1/n here, such that in the end we'll get the total amplitude here. But probability amplitude 1/n, it's probability 1/n squared. We have n times 1/n squared. It's around the probability of the explosion. If this is a bomb, it's 1/n, and making it very long, we can make it as efficient as we wish. Now, the same story can be done here. I can translate this picture to this picture. Now, in fact, people kind of combined this efficient interferometer and found this communication, because this is communication of 1 and this communication of 0, but this is not. Every time we have a different device. We need one device which will be able to send 0 and 1. Bob should put or not put, and he has a different device. So this is not good. But Salih and was apparently the one who found the idea of how to make this, and this is kind of very big interferometer. You see, it's kind of double Zeno effect. There is this big external interferometer which slightly go here and here, and inside there is a big chain, and it's all like this, that if there is nothing, this go out. So if there's nothing go out, this is like it cannot continue here, so it's left on this side. So in the end we get it mostly here. But if we put here this big shutter, it every time something stay here, and then in the end everything it will be on the right. In the end, in fact, we can arrange. It cannot come here, it will always here. So the bit 1 will be with certainty. And mostly it will can bit 0 if it will not put anything. Sometimes it can make an error. But in general, we have information can be transferred between Alice and Bob without any physical particle traveling between them. Protocol for direct counterfactual quantum communication. Now,
between that and the Zeno effect?
They use Zeno effect to make it efficient, because every time, how does this operate? Because of the Zeno effect, it's like the photon can go from left to right. Here it has small chance to go to the, and since we test did it go, it doesn't, and we test many times, so it's never go. This is, yeah. Yes.
If you ask in terms of information paradox, you still need to wait some time. Although there is no particles, this goes from A to B, you do need to wait time for, let's say that A and B are far apart, you need to wait some time until the communication takes place, right? It's not instantaneous, the transformation information.
I believe nothing can happen faster than light, and of course we have this light. This light go from here to here. We have this, and there is a channel. This channel has all this transmission channel is here in between, and there are many things, and we have to wait until the photon could go there. But in case of our success, when Alice got this click, it was traveling on her side, so it still take a long time. All the thing. And the Zeno takes a time. So with Zeno we get a high efficiency, but the protocol is much longer. We have to use many interferometers. Maybe for credit issues, there is this protocol for direct counterfactual communication, and this is 2013. At 2006, there was another work which counterfactual quantum computation through quantum interrogation. Very different name, but exactly the same protocol, 1-to-1. And in fact, they kind of cite them, but I don't know. So then, moreover, the Zuberi, and in fact Salih too, they made a step forward. In all this, we transmit classical message. You know, here there is some message. Bob put something or not put something. But essentially, with some more exercise, Bob can put a quantum object here. And then Alice can get this quantum state. And this is what was written in this paper. And then recently, you see, unknown quantum state, bidirectionally teleported in the process of information exchange. There is no physical particle traveling between two communicators. So it's teleportation without arranging entanglement channel before, without classical, great thing. And moreover, recently Salih, I think, found something which is probably feasible to implement it. So he had a method how to do this. And again, some credit issue. If you see, the Salih was a kind of collaborator here on the counterfactual communication. He, for some reason, is not here. Although there is a preprint of Salih with the same idea even before this paper. But it's not my business. It's still partly my business because, just to say that here they say where sender and receiver transport of an unknown qubit exchange no particle. This is, I think it's kind of feasible experiment. My business, because I had something to complain about this paper, and I had something to complain recently about this paper, very recently, this year. But let's put aside my complaints. We can summarize it in the following. We can find an opaque object without a probe interacting with it. We can find that the object is absent. There is nothing here. Without particle being here. We can transfer a message without particle in transmission channel. And we also can teleport. We can transfer a quantum state without particle in the transmission channel. Yes?
This means that with the Zeno effect, the bomb will never explode. If you put the bomb at the bottom of the Zeno chain, it'll never explode.
Never not, but with probability roughly like 1 over n, where the n is the number of your elements, large elements. So, like all Zeno. Zeno doesn't prevent it 100%. You can prevent it with a high probability. And what I will say, my mistake was why I thought you cannot make interaction-free measurement better, because I thought to find interaction, to find a bomb, you need a bad word in which there was an explosion. So when the weight of this big bad word was equal to the weight of the good word, I was happy. So I thought the 50% is maximum. I didn't realize when there are many bad words, and well, how there are many? Because it can be exploded in different times. This is how we get different bad words. So when there are many, then all what we need equal amplitude. So and the probabilities of if you have many bad words and one good word, so we can put amplitude of bad words together equal to the good word, when the total probability of bad words is very small when there are very many. But you know, I felt at least that it's too good to be true. This is. And again, my main problem is here. I was kind of happy with this story, but is it really true that this is interaction-free? Interaction-free means that the particle was not here. So I started to think how to talk about where is the particle, trying to publish a paper which was difficult to publish. Then I said, let's make an experiment. Ask photons. Ask photons where they have been. Not because now how you ask photons, they are not necessarily very intelligent. So the way to ask photons is the following. In one place, you give them some information. And if you detect this information in your detector, through this, absorbing these photons, then you know the photons have been here. So what we did, we put some frequency, some wiggling here. With this wiggling, this mirror. So the ray go up and down, and here we have kind of two double detector. And we have a signal, the intensity up minus intensity down. Clearly, the signal will have the same frequency as the wiggling. And we can make a Fourier transform and see it. And yeah, if this is this frequency, we saw this. So this is how we ask photons where it have been. But of course, here we know, yeah, clearly the photons have been here. It couldn't come any other place. There is no question. But we wanted to know where it is inside interferometer. Something which Bohr said don't ask. But this is what we want to know. Where was the photon inside interferometer? The photons which come to here. This is a detector we put only in this output port. So we put wiggling with different frequencies in all mirrors. Here there are many mirrors. And we got this signal. This beam splitter put 2/3 here, so this is why here we get bigger signals than here. And then 2/3 here, it will be 1/3, so all these signals are kind of equal. This interferometer first we tuned to constructive interference. This is how it goes. So, but this is kind of just testing that our method works. We were interested not in this.
Are these photons identical particles? They have different frequencies?
In fact, there were experiments later, which instead of putting this vibration, in fact I will mention one, they put some modulator which changed frequency. Here I don't talk about the frequency of the photon. What happened, our beam goes up and down. So when the photon comes to particular mirror, then because of this wiggling, the beam go up and down, and so it go come out here up and down.
But then the destructive interference doesn't work anymore.
Yeah, they need to overlap.
Yes, but the beam was about 1 millimeter,
Yeah.
and the going up and down was less than a micron. So the interference almost, at least in our experiment, we didn't see any. In principle, the interference slightly. There is some problem, but when it was very tiny, so interference remained more or less okay. Okay, so the experiment which we are interested was this experiment. You see, this is essentially this is what I was looking for. I have inner interferometer which go out, and then I have external interferometer. We can call it, this is A, B, and C. The C is the external one. In the inner, we added 2 more mirrors kind of to analyze what's going on. Here there is mirror here missing and mirror here we cannot test. But essentially, I was asking if it's here or not. So essentially, if it's here or not. This is what I wanted to know. Now, this work made some noise, so I'm pretty sure some people here know, but if people never heard about this work, please, somebody give me, well, what do you think? I didn't show yet the result. You know, kind of the obvious result is C, because this seems to be the only way to go. But if I ask, it's not, should be C or only C. Because everything which go here go out. Yes?
But you need to repeat the experiment many times, no?
In the run, to make the Fourier analysis, every run was like 3 seconds, and like 10 to the 13 photons comes through.
It's not a single photon experiment, right? So
It's not a single photon experiment. There was similar experiment with kind of single photon, because they use another modulation, and on they could know every photon if it were it. But this is not a single photon experiment. But the idea is that they're all the same. So I believe that if I understand all physics and I find that they have the same property, I find it on the ensemble, so I attach it to every one. This is a big question. Of course, you know, this is $1 million question. If you have a photon through 2-slit experiment, does it go through 2 or through each one? I don't answer this question in this experiment. So, any suggestion where my photons told me they are?
Probably only C.
All of them.
Yes,
Why?
Because you are detecting that. You're not detecting all of them, you're detecting some of them, and those whom you ask, they know, and those who do it, they don't.
More till now, it's not what the photon told me. The C, C is very natural, and this is what, in fact, Wheeler, I think, discussed against Bohr where the photon was, and he would, unfortunately, I had a discussion with Wheeler, but I didn't know what was my idea to ask him. But from his work, it looks like he would say C. But
detector is only at C.
what?
Maybe
Detector is only at C.
Detector is here. We look, again, there is detector, and it looks like the light to detector come only through C, because it looks like it doesn't go through here. But If I ask, so any proposal? So what? So please say loud what you think.
Maybe C, B, A, and E.
A, B, C, and E. Everything except that. Okay, this is what we have seen.
Oh, no E.
No. Which is, maybe. So, and this is kind of strange. Because how we can get how the photon was here without being here? This is kind of strange. And even before making experiment, my definition of the photon, where was the photon, is where it left a trace. This is slightly different. It's where we affect the photon that we see how we tell us where it is. But I think every photon, when it goes, it kicks mirrors. Of course, it's the uncertainty, it definitely, momentum of photon changes, so it kicks this mirror. Why mirror doesn't know, why can we have interference? Because uncertainty in momentum of a mirror is much larger than the kick it gets from the photon. Still, the quantum state of a mirror changes. So I can ask, which mirror changed the state? Where there is a trace? This is from ideal trace, and my analysis said that, so my definition was the particle was where it left a weak trace, and the weak trace I think was inside inner interferometer on these mirrors, but not here. So not here. So very strange how.
Why? I didn't understand. Why wasn't there an E? Why
So
didn't
exactly, this is very difficult to understand. So since it's very difficult to understand, the only way to understand it is really the two-state vector formalism, which I think is a good idea to study it, because of course everything can be calculated from entanglement, whatever, forward in time normally. But to see it, to get intuition and to get the answer immediately, you can use two-state vector formalism, which started by Aronov long before I came to do a PhD, and we can to push it forward in '64. And the two-state vector formalism says that if I have a system between two measurements, then we should describe it not just by quantum state from the preparation, like the normal one, but also we have to add this backward evolving wave function from the future measurement. So we have in between it described by two of them, pre-selection and post-selection on equal footing. They're really, if it's complete post-selection and complete pre-selection, there is no difference if we want to discuss. Both of them are very important. The two-state vector, this is what describes my system here. And then to get any kind of effect on an environment, we need both. If there is only one, the particle is not there. So the weak trace, we can calculate the weak trace which can appear only in the places where the both forward and backward wave function. So we can analyze this story and to see where is this weak trace, where is this two-state vector overlap, and this will tell us where we might expect a weak trace. So this is the wave function which we saw before, the forward. You see, this is the interference going here. And now we got a click here. In our experiment, we consider things which go to this port. So we have to start with photons which start here. The photons which start here, the backward wave function is the same Schrödinger equation, just backward in time. And you see, it's all unitary. If everything entering here, go out here. So if it will enter here, it go here. The backward, so it should be from here, must go here. It cannot go here. Because this was 100% tuned interferometer from here to here, and then of course clearly from here it should go up out here. So now let's look on two together, and we see the overlap is inside and on the left, but not here and not here. So this is where I should expect weak trace. Now the weak trace, there are a lot of discussions. Some people like, some people don't like. I think this is the main story for me. I think I was there when I left a trace. If I gave a talk somewhere, some people remember me, and this is where I was. But
so if you put a bomb over there, it will never explode.
So I will add some more thing. If I'll put a bomb here and I get a click here, I know that the bomb will not explode. So another, in quantum mechanics, unless you Bowman, and I don't think there is any Bowman here, particles don't have position. When you study quantum mechanics, it's wave. We shouldn't ask where they are. But kind of the idea is that we can find the particle. So one, I think, not so bad definition is that if we introduce non-demolition measurement in particular place, given the pre and post selection, if it can click, so the particle was there. If it cannot click, the particle was not there. And but here we're asking about this place. So if the photon left no trace, so it wasn't there. But if we'll put here non-demolition measurement, and today at least RAMP and MPQ doing this kind of thing, looking on a photon in flight and let it go. So if we'll put such a detector here, in fact the calculation will tell me I will find it with certainty. If I will look here. So if I'll find it with certainty, also I will find it with certainty too. But here I thought it is, because this is kind of normal. But here I also will find it with certainty. So it's very difficult for me to say that it was not here, but it just was here.
But how do you find it if you already know that you will detect it later at detector D? You only sent one photon.
I sent a single photon, which today maybe the first. Then I look on every experiment when I find it here. Here in the addition non-demolition, it's a photon. So my detector will make a sign that it was there, but it let it go. Of course, the picture will be different. If there is this detector and it may click, I will not try this trajectory. Given this, I will say, oh, the trajectory was probably like this or whatever, if there is trajectory. I'm against the principal trajectories, but I can say trace. If I will add this non-demolition measurement, I will change the trace. This is true. But the idea is I still can get a click here. This is non-demolition. I let the detector let photon go through. Just say it was past near. Okay. So,
but if you let it go from this detector, it will go in the forbidden path, right?
It's if you
here.
Yes.
You see it and you unleash it, right?
Yes.
You let it go, and then it can go to B or to.
No, it can go to D definitely, because you see now. When I found it here, there is no destructive interference. I found it here. This is how I allowed this.
Okay.
But it seems I'm kind of trying to be. I want to at least to get that there is more stories. So interaction-free measurement that the place is empty is not interaction-free. This is what I say, because there is a trace here. I can find a photon here. So, but maybe it should be important to mention that interaction-free measurement of presence is okay, because I look on my overlap, I don't see overlap. There is no overlap of my photon here. Here it's forward, here it's backward. It's not here. The photon was not here. So if I will try to look for it here, I will not find it. We know that the shutter is in O, but the photon was not in O. No way to find it here. No problem. So at least one part is the original interaction-free measurement is still fine. Let me try to. It's
crucial.
What? Crucial? Yes.
How do you reconcile that with the Schwinger Dyson problem?
Let's discuss it after. Okay. Okay. Non-demolition measurement in O, if performed, would certainly not find the photon. So this is interaction-free is fine. So then I say too good to be true. Apparently I was right. everything disappears except this first part. But then I was talking to Yakir Aronoff about this, and he was not happy. And I explained in this case, and he tried this, and tried this, and tried this, and then in the end, we got this new idea. Let's replace our nested interferometer by double nested interferometer, and replace the task of sending the message by blocking two places, one after the other, or not blocking. So, still, the protocol says that if Bob wants to send bit 1, and the main thing was that Bob wants to send bit 0, that there is nothing here, but the promise is either we block two places, one after the other, or not. And the interferometer are kind of very similar to the original one. You say nothing go here, else of this, it will not continue here. But if we block both of them, we arrange that this detector cannot click. So it can click only when both are empty. And there is a promise, either we block two or block nothing. So when we get click, we know that it's empty. Why it's better? Because when I look on my forward and backward wave function, the forward go inside the first one, the backward go inside the second one, but they do not meet. So the only overlap is here. So if I'll calculate the trace in this experiment, when there is nothing there, the trace is here, it was not here. Moreover, you remember I said that I didn't like the other one because if I'll try to find it in O, I would find it with certainty. Here, if I'll try to find it here, I will definitely not find it. I cannot find it here. If instead I will find it here, I also will not find it. So it looks like it's great. I cannot find it, there is no trace, so we succeeded to do this. So now I can take my counterfactual communication and repair it, make it its double, and now of course it will be even less efficient, but when it works well. It works in counterfactual way. And in fact we also made in China, we made an experiment demonstrating this story. It was instead of Mach Zehnder, it was Michelson-Morley, but the same idea. This was transmission channel, this is with closing, and this is with not closing. And you see this channel was A. In both cases, we didn't see A. You see, here and here A. So we also tested, we made this the protocol, and we tested, was it there or not? This was kind of putting some sign on the photons. If they were in this channel, then we would see this change of frequency, and we didn't. So everything looked good. Moreover, in principle, we said that all other experiments could be repaired by this. Just repair. Take instead of this, put this, and then everything. All these papers, some of them complained that they are not good, but now they will be good with this patch. So, conclusions: everything is good, but. So, I still had worries. So, what is my worry? It's kind of new worry which I didn't publish yet. Probably have to do it quickly. You see, what I say, the photon was not here. If I look here, we will not find it. The photon was not here. If I look here, I will not find it. And this is kind of the property. When it's interaction free, when the photon is not present in the transmission channel, it was not in a both place. But the protocol was talking about putting in two places or in no places. So the right question is to ask, was it in two places or not? Of course, if you think classically, if it's not here and it's not here, clearly it's not in two places together. But quantum mechanically, this is not true. If you ask, put these two non-demolition detectors, then definitely at least one of them will click. Quantum mechanics is different than classical. Classically, I know, if I look only here, I definitely will not find it. If I look only here, I definitely will not find it. I look in two places, I definitely will find it somewhere. So I cannot say that my photons was not on both sides. If it was on both sides, then I cannot say it's interaction free. Now, I really, this is kind of classical test. If I made it, I less like it. What I liked is my trace phenomena. I say that when the particle leave no trace, it's not there. If it leave a trace, it's there. And it doesn't leave a trace. The first order trace is not here, and the first order trace is not here. But the information which is important is worried in two places together. If I will really send a real particle here and then later here, it will leave a first order trace here and leave a first order trace here. But information about presence in two places will be second order, because we need orthogonal component from here and orthogonal component from here. So even the real particle will leave a trace of the second order about presence in two places. And in our experiment, there is a second order trace. So eliminating the first order trace is not enough. The signature of presence in two places is a trace of the second order.
5 minutes.
Yeah, so I speed up maybe too much, because essentially I kind of conclusions too good to be true. Yeah, they are too good to be true. We're left only with this. However, even this, I think it's pretty amazing. And apart from kind of interesting game, I think it has a real practical application. It's enough to just consider the blocking. What I cannot do, I cannot find that the place is empty. But I can use only the protocol in which I use blocking only to get something very useful. What I can do with this, I can do a counterfactual key distribution, which relies on this part, which I say is still okay. No problem with this. This is really counterfactual. I can find that the block something is here without being here, without leaving any trace whatsoever in this region. So how I make, there is Alice and Bob, and they want to have a secret key. How they arrange the secret key? They have two systems like this, and maybe it's better to, in principle they can have even the single one, but the efficient one is more efficient. So let's do it more efficient. So they have this interaction-free measurement of presence of an object, this big interferometer. When you block this part, then this cannot click. If it's not blocked, this can click. So, and this cannot click. So the only way to get a left click, the only way to get a left click is when it's blocked and we have a photon here. So the protocol is following. There are two devices, one called bit 0, another device called 0 to 1. Alice randomly put photon in one of them, maybe here. Bob, far away, randomly put block in one of them. Because all these devices, there is some part in Alice, the big part, and some part in Bob. And there are two like this, one's called 0, one called 1. Alice put photon in one of them, Bob put in another one. They far away, they don't know which one they put. Then, in the end, Alice get click. If they put it in a different one, it will be a right click. So when she gets a right click, she does nothing. Then she does again. She puts and Bob put. And then you see, it's still different one. She put it in 0 bit, and Bob put shutter in 1. And then it will be again right. Now, sometimes it will happen that they will put in the same one. If they put in the same one, then Alice usually will get this forbidden click. And then she said, she sent a message to Bob, I got the left click. Now, Bob knows that he put 0. Alice knows that she sent the photon 0. So they have this common bit, 0. If in between cannot know anything, because she has these two devices. In this transmission channel was nothing because no photon was sent. In this transmission device was nothing because it was good interaction-free measurement with the shutter. When also in the transmission channel there is nothing. So for if there is no difference whatsoever here and here, but for Alice and Bob, we have this established, we establish a key, and this is established in purely counterfactual way. Yes.
But if in this case Eve is putting a non-destructive measurement, Eve will know.
So So the counterfactual key distribution is a great conceptual thing. I can be extremely amazed that I succeed to make a key between Alice and Bob without any interaction. For practical purposes, is not better than others. This is absolutely good for passive if, which if comes later and look on channel. If if is active, then security of counterfactual doesn't change the security of the standard procedure. It's for conceptual reason it's good, or for passive that when during the sometimes when some passive if also can do something. For passive if it's 100% proof, but for active if it's not better than others. So conclusions: we can find an opaque object without probe interacting with it. We cannot find a place is empty without a probe being there. The past of the particle defined as a first order trace can be disconnected region. For me, there is a trace here and trace here exactly the same, and here there is no trace of the first order. There is a trace of the second order, but it's kind of secondary presence. But I would say that the particle is present in 3 places. I like it, I don't have problem with it. Some people don't like that the particle doesn't have trajectory or can be in 2 places. But using the definition, the particle where it left a trace similar to the trace of a single particle, we get this strange picture. We can transfer a message without leaving the first order trace. Interesting, but maybe not so surprising, because first order trace is not enough for this kind of the method when in 2 places, and the 2 places the second order trace would count. This is what they said, but we can do this. We also showed by experiment. And we can transfer a secret key without particles in the transmission channel, which I think it's kind of a miracle. And this miracle let me believe there are parallel worlds. It cannot be, because if you are lucky in the first time you get it, you get some connection between Alice and Bob when nothing goes between Alice and Bob. This is against science. All science tells there is some causal connection. Here nothing goes between Alice and Bob, and you establish secret key. So I think this is a profound concept. Thank you.
Thanks a lot for this very interesting talk, and there were really many questions. I'm sure there are many more, but we don't have much time. Nevertheless, maybe a couple of urgent questions.
How do I know it's urgent?
I decide. I look at your face. If you are really under stress, then it's really urgent.
When you say place, does this place have a size or?
It's, there is a place. If I cannot find a particle in a complete 0 place because it's immediately later. So here I will kind of use it in this arm of the interferometer. This is what what that means.
I'm not sure it's urgent, but I'm just a little bit confused. So what's the difference between this and the classical double slit experiment? So we have, let's say I have light going through these 2 slits, and I'm I'm sitting at the minimum where essentially there is no light on the screen, right? Now, if somebody comes and closes one of the slits, then I will see light, right? Yes. And so what's the difference between this and the bomb thing?
When you see light, there is a photon which really goes.
Right.
You get a click. You get. Here, Bob doesn't get. Bob, someplace he put a shutter. There are all reasons to believe that where he put a shutter, there was no photon. If it was only single particle, the photon was not, in your world, the photon was not there. Right. Here, and this is strange, and still Alice gets information. Alice has some photon traveling on her side, which could go to the Bob, but it didn't. Because if it would go, the Bob, it will not come to her. She finds it. So she knows the photon was always doing some zigzag on her side. She gets some click, she knows, Bob put shutter. Even the photon was never there. This is what's strange. In your example, we had a real photon which coming from Alice to Bob. Nothing like this.
Why? I don't understand. If both slits were open, then I get no photon.
If you have a promise that something is sent, and you open 2 bulbs and she did no click, she knows, I know that the bulb was open, but there is no any promise here. It can be in any time. There is no promise when in this particular time it was sent. But just sometimes there is this, that Bob should put it for a long time.
Quick question.
Yeah.
So you mentioned during your talk that a photon doesn't have a position. To have this dynamics where you release it from some space and measure it at some other place, you need a wave packet.
Exactly. Yeah.
Is there a description of this whole formalism in terms of wave packets?
It's all kind of, the experiment was we have a coherence lens and whatever, and then some other experiment, the Chinese experiment.
I understand, but
theory. Yes, it's all the photon doesn't have precise position, but has a wave packet. So one can say when we have a single wave packet, we think, oh, it's inside this wave packet. Here it's split. Now there is a wave packet here and here and here. This is why what I mean. It's in 3 places. A wave packet and 3 arms. And if these are fibers, then it's pretty clear where they are.
Okay, thanks a lot. Okay, we'll see you all next week. אני חייב לדעת שמה שמעתי איתך, בעקבות החלק הראשון, נותקר אחד לא, מצוין. אתם מכירים? ספר, בוא ניגש לפיזיקה.
יש לי פוטון אחד, הוא התחיל מפה, הוא הגיע לפה. עכשיו אני שואל, איפה היה, מה הוא עשה, איזה מראה הוא עשה אני אומר, פוטון שיצא זה הירוק. כאילו, עד לפני ישבנו בשלושת המקומות האלה. אז אם אני אשאל עליו, אז אני צריך להסתכל פה, הפוטון שנמצא פה, אני אגיד לא, זה לא רלוונטי. למה? מפני שהפוטון שהגיע לפה לא היה פה. אז לכן, כשלדבר מה הוא עשה, אני צריך להגיד איפה היה, איפה יש באוברלאפ הפוטון שמצאנו, שיצא לפה. כדי שאני אשאל מה הוא עשה לדברים אחרים, אני אצטרך רק במקומות איפה שיש גם וגם. אני אגיד שהמראה הזאת קיבלה מכה, המראה הזאת קיבלה מכה, הביום ספליטר הזה גם קיבל מכה, אבל זה לא. עכשיו, אני לא אומר שכאילו, הזמנים זה אותו זמן, כשאני מחשב, אני הולך אחורה בזמן, יש פה איזה זמן מסוים. אז אני מחשב מפה עד לפה, וכשפה אני הולך אחורה בזמן, זה הזמן הזה. אני שואל איפה הפוטון היה ברגע הזה, אז אני לוקח מכאן פורוורד עד לפה, ומכאן בקוורד עד לפה. עכשיו, בעיקרון הפוטון הזה מפה כאילו היה בשלושת המקומות, אבל פה זה לא רלוונטי, מפני שזה אולי פוטון אחר, אם היה נכנס, אז זה רלוונטי, אבל הפוטון הזה, שהתחיל מפה, לא היה פה, לא הגיע לפה.
אני שבוע הבא לא פה, ושבוע הבא זה
תוצאות שעבר דרך אותו סיכוי של שליש מ-A, B ו-C.
שפה עבר, אני אומר שהוא עבר גם וגם. שאני ונסטת
בסדר גודל יותר ממה שקורה פה באנגליה, אינסטלציה כזאת.
כאילו פשוט זה זז קצת, ימינה קצת, איפשהו נמצא.
אז עכשיו, הטענה היא גם, שהיה לי פה את החלק, אבל לפעמים אני אומר, למה הסיפור, יש הרבה מאמרים, תוקפים אותי, לא הגיוני. אם אני קיבלתי פה, וזה ככה, לא יכול להיות שהיה פה. אז עכשיו, למה אני אומר? אתה רואה, אין המשך. זה הפורמה, אין המשך. עכשיו, כדי להגיד למה שהם לא צודקים, למה לא יכול להיות ש-A לא יותר טוב מזה. אני אומר, בואו נתאר את המצב הקוונטי שהגיע לפה הירוק. המצב הקוונטי הירוק זה בדיוק ה-3 box פרדוקס. זה A פלוס B, זה המצב. עכשיו, המצב שאני בודק פה, זה מצב קוונטי. אני יכול, במקום לבדוק אותו פה, לבדוק אותו פה. אני הולך אחורה בזמן, אני אומר, מה שמגיע לפה, זה הגיע מפה מאיזשהו מצב מסוים. עכשיו אני גם יכול לבדוק אותו פה. עכשיו, המצב האדום הזה,
תבדוק אותו פה.
אז עכשיו, כן, למשל...
אבל עדיין יכול להגיע לגלאי כזאת.
לא,
כמו שלושת הקופסאות,
אני כרגע
וכאילו פתחת את הקופסה.
שכחתי מהדבר הזה, אני רק מסתכל על כל הפוטונים שהגיעו לפה ואני בודק מאיפה יכול היה להגיע. ואז עכשיו יש פה, ואז אני אומר שהפוטון הזה 100% אני עושה unit revolution backward in time, ופה יש זה בעצם שני שליש A שורש, לא, שליש A ומינוס שורש שני שליש כאן. אני אומר שלבדוק אותו פה ולמצוא אותו פה זה אותו דבר. כל המדידות שאם אני מוצא פה שורש שליש ופה מינוס שני שליש, זה אותו דבר כמו למצוא אותו פה. עכשיו אני חוזר עד לפה, רק נקודה. כשאני מגיע לפה אני אומר שהמצב בעצם שמתאים לזה, לא סתם. זה A מינוס B A מינוס B פלוס 4. זה מינוס מפני שפה מינוס, אתה רואה? מלמעלה זה פלוס, מלמעלה פלוס, מלמטה זה מינוס. עכשיו, זה מינוס ב-B, פה זה פלוס O ופה זה פלוס O. כשאני מתאר המצב הקוונטי של הפוטון הזה בשני הצדדים, זה אותו דבר, זה סימטרי לגבי A ו-O. אז אני לא יכול להגיד שהוא פה ולא פה.
אני מבין את זה ברמה של פירטים.
יש פה פוטון אמיתי.
אני יודע. הפוטון לא יכול לעבור מפה בעצם. פוטון אמיתי אני יודע שהוא יכול ללכת רק ככה. אבל אתה אומר בעצם אני יכול להסתכל על מה הפרובביליטי שהוא נמצא בכל מקום.
את השפה הזאת אני אף פעם לא מקבל, אבל הוא נמצא בכל המקומות, אין משמעות שהוא נמצא פה, אין פרובביליטי, הוא נמצא בכל המקומות.
אבל אתה חייב להביא אותו להכנסה.
אין דבר כזה.
אני
בכלל לא חושב.
כל פעם
וואי, חובה קולקוויום.
תודה רבה.
תודה רבה.
ביי אלי.
ביי אלי.
שבוע טוב.
היי, שלום, הייתם משהו.
תסביר לנו על הפצצה של וייבר וליצור, אני בישראל, בגלל ההרצאה הזאת אני כבר רציתי להגיד תודה, פעם לא יצא לנו להיפגש, ובסדר, לצערי לא אספיק אבל פשוט יהיו לנו הזדמנויות. אז תודה רבה, זה היה מרתק.
תודה לך.
אתה יודע, אני כבר כמו לב, אני אמריטוס.
אני
אמריטוס יותר זקן.
אתה יכול להסתכל פה.
שמים לב.
שווינגר דייס, אני אבוא ויגיד, אוקיי, אני יכול לשים פה אופרטורים, סדר אותם לפי הזמן.
נכון, זה גם בסדר.
אני לא מתבייש להגיד מתי שאני לא בקיא, אבל אני לא חושב שיש שם משהו ש... אני לא אוהב אופרטורים בכלל, אני אוהב פונקציית גל בלבד, כשצריך אז אני באבולוציה, אופרטורים, כאילו, קצת הסתכלתי, לא הוסיף לי.
אני התפלאתי שלא עשו את זה עם...
אוקיי, בסדר, תודה רבה, הייתה הרצאה מרתקת. תודה.
הוא ענה על השאלה, אם מזיזים את המראה.
כן.
שזה עושה דיסטורשן של המראה. אבל אתה יכול לעשות את זה עם דף, אתה יכול להזיז את המראה.
עם דף, כן.
במסלול של הפוטון, אז אתה לא מקלקל את הפרמטר, ואתה יכול להסתכל על הפריקונסי.
זה ניסוי יותר עמקי.
זה ניסוי.
אני חושב שבאמת ראיתי עניין.
כן, באו אנשים במיוחד מהנדסה.
פרסמו על זה פייפר תיאורטי,
סטודנטים מהנדסה.
כן, אבל אם אתה מדבר, תגיד לו, אם יש לו רעיונות, שיבואו, מעבודה שלי פתוח.
קולוקיום בתל אביב, אין יותר קהל.
אני חייב לדעת שלא כל שבוע יש לנו קהל כזה יפה כמו היום, אני חושב ששמעו שאתה מגיע והיה צפוף במיוחד.
אני שלחתי אימייל לאבי אבל הוא לא הגיב.
אבי,
לא, אבי שכאילו כיכב פה בטוק, אז חשבתי שזה יעניין אותו.
המקום פתוח.
לא, שלא יערוץ, אם יש הרבה סטודנטים.
יובל שואל אם הוא יכול לשבת גם בצהריים.
כאילו לא תשלם בעצמך,
אבל... לא תשלם, אם יש הרבה סטודנטים, אז...
לא, זה טוב.
כן?
כן.
אז רון, תחבור אליו.
כן, אני אדבר איתו, אמרנו שאתה לא...
אז הם יוצאים כאילו בעוד חצי שעה, זה לא מיד, במשרד שלי. תבוא ב-12:30, 209. בבניין הזה, 209. קומה 2, משרד 209. תבוא לפה.
בחרתי שעברת, אבל לא...
כן.
הגעת לי לראות.
טוב.
נתראה.
צריך טלפון, אבל לא צריך להיות על שקט.
כאילו שלימדת פה פיזיקה 2 עכשיו.
מה?
כשאתה מלמד מהנדסים.
רוצים שאלה בפיזיקה 2?
לא, בוא נדבר על קוונטים.
זה לא פיזיקה 2, פיזיקה... זה סתם...
מה השאלה?
יש לי בלון היליום. אבל יש, אתה יודע, לפעמים יש בלון בצורה של קובייה.
כן. אוקיי.
אז יש לי בלון בצורה של קובייה. ואז אני שמתי פה היליום, אבל לא הרבה.
אוקיי.
ואני מסתכל על הפאה, ואז אני לוקח את החוט, מוליך, ושם אותו לוונדרגרף. ואני שם עליו איזה 100 קילו וולט.
אוקיי.
ואז אני מסתכל פה אני רואה שזה פלט, כדי שהוא כאילו, ואז אני מודד פה ואני רואה שיש שם סיגמה, צפיפות מטען סיגמה.
אוקיי.
עכשיו יש לי ברומטר בחוץ ואני יודע שיש לי פה P0, זה האטמוספירה בחוץ. מה הלחץ של היליום? יש לי משטח שבמקום שהוא שטוח,
כן.
זה משטח אלומיניום כזה, כאילו, זה לא גומי.
כן.
הוולטג' שלו, יש וולטג' גדול.
רק הפאה הזו?
מה?
רק הפאה הזו שטוחה?
אולי יש שמות, אבל ראו חלק.
זה בטוח.
אז יש שם מטענים כאילו על הסרפייס, זאת אומרת, יש איזו דחייה כזאת של הפאות דוחים אחד את השני.
הפרש המתחים הוא בין הפאה הזו לפאה הזו? איך אתה מסדר את ההפרש מתחים? את ההפרש פוטנציאלי?
אני מקשר, לוקח...
סוללה ומחבר לכל הפאה
זה
הזו?
לא סוללה, זה ואנדרגרף. אתה מכיר את הניסוי הזה עם השערות של הבנות?
לא, זה ואנדרגרף.
זה עם מחזיקה בלון.
אני יודע, יש פה 100 קילוואט.
זה בערך 100 קילוואט. זה בערך מה ששמים שם.
באמת? כזה חזק?
כן, אתה לא יודע?
חשבתי שזה חלש יותר.
לא, זה המון. זה בערך 100 קילוואט.
טוב.
אבל מה שנתון לך זה סיגמה. זה לא נתון, סתם כאילו. זה אחד קשור לשני איכשהו.
אז מה התשובה? צריך לצפות? זה מצחיק כי בהקשר לשאלה הזאת, חבר שלי אלסנדרו סילבה, אז הוא פרסם בפייסבוק שהוא התווכח עם הילדים שלו איך ייראה אגם אם העולם היה קובייה. זה קצת קשור לשאלה הזאת, אולי קצת שונה גם, אבל אם כאילו בכוח המשיכה, אם העולם היה קובייה, אז איך המשיכה הייתה נראית? לא, זה קצת קשור. יש שם קובייה, אולי זה ההקשר היחיד, אבל...
אני מרגיש שהתשובה לא תלויה בסיגמה.